So we're going to start chapter 13 by looking at radical reactions. And this is a little bit weird because radical reactions don't react the way that most of our 2-electron chemistry does. So last semester you learned how alkenes react, you learned about substitution reactions. All of those were 2-electron processes. A pair of electrons did something. Radical reactions involve single electron processes because radicals have single unpaired electrons. And because of this, that's not something we see in normal chemicals, normal molecules. Because of this, this makes them very, very highly reactive. So even though this isn't something we see all that often, so if you're learning a new reaction, most likely it doesn't involve radicals. It is very important for biological chemistry, materials chemistry, atmospheric chemistry, because radicals play a role in a lot of very important processes. So let's look at an example of a radical. So one thing, like I said, that's important is that they have unpaired electrons. So let's look at tert-butyl radical as an example. Here we have a single carbon with 3 methyl groups coming off of it and one single electron. That electron belongs to this carbon right here. Now, one thing to notice here is that this carbon does not have a full octet. It only has 7 electrons, and that's why it's so reactive. But it does have 1 electron from each of the 2 electron bonds and a single electron. That's 4 electrons total, so it has no formal charge. So unlike carbocations that you saw last semester, unlike carbanions, these carbon radicals have no charge. Thinking about things that we talked about in our review of 331, this is an sp2 hybridized carbon right here, which means that we have those 3 bonds to the methyl groups are all in one plane, and the unpaired electron is taking up a p orbital on its own, an unhybridized p orbital. We call this a tertiary radical because the central carbon, the one with the radical, is connected to 3 other carbons. A secondary radical might be something like this, where the carbon with the unpaired electron only has 2 carbons attached to it. And then a primary radical would be one in which the carbon with the radical only has 1 carbon attached. So that might be something like this. Let me draw hydrogens in here. Otherwise, this skeletal structure gets very awkward. And then you could imagine having a methyl radical, which is one where we have a carbon with 3 hydrogens attached and no other carbons attached to it. So these are our types of radicals. We'll learn more types of radicals later, things like allylic or benzylic radicals. And in terms of general stability, the trend is that if we have more alkyl groups attached to the carbon with the radical, you get a more stable radical. So this is the most stable of these radicals that we've seen so far, and this is the least stable because the alkyl groups, the carbon-hydrogen groups, can contribute their electron density to help or assist the electron-deficient carbon in the center. This is the same trend you saw for carbocations when you were introduced to those, and it's for the same reason. Both carbocations and radicals are electron deficient. But there are significant differences in behavior between a carbocation and a radical. And one difference is rearrangement. So in 331, this is review, if you had a carbocation such as this, you might expect it to undergo a hydride shift to create a more stable carbocation. So you might expect this hydride to move. And in doing so, you'll go from a secondary carbocation to a tertiary carbocation. So in this, we have the positive charge on the tertiary carbon. This hydrogen has moved over, and we've gone from a secondary carbocation to a tertiary carbocation. And that might happen because this is more stable. If we had the same sort of thing with a radical, though, that secondary radical would not be able to rearrange. Instead, what it's likely to do is to find some molecule with a weaker carbon-hydrogen bond, or with a weaker bond in general, and react with that. Because remember that our radicals are highly reactive. They just don't do this specific chemical reaction. Now that we've talked a little bit about radicals, we're now going to talk about where radicals come from. And most frequently, they can come from the cleavage or breaking of a CH bond. And since most of the organic molecules we look at have multiple types of CH bonds, we really want to keep in mind the connection between the strength of a CH bond and the stability of the radical. So here we have a general rule, and this is going to be true, forever. More stable radicals are going to come from the cleavage of a weaker CH bond. There's a direct connection between the strength of the CH bond, because that strength is measured by the radical dissociation of that bond, and the strength of the resulting radical. So if we look at this simple molecule here, we have 3 carbons, we have 3, 6, 8 hydrogens, but we only have 2 unique hydrogens, the one I show in red and the one I show in green. And so let's show how we break either of these. Again, an important thing with radical chemistry is that radical reactions involve the movement of 1 electron, not 2. So to show that, we use these fishhook or half arrows. So here we have this 2 electron CH bond, 1 electron is going to the carbon, and 1 is going to the hydrogen, to give us a radical on this carbon plus an H dot. That's a radical on a hydrogen. We can do the same thing here. And what we see here is that we get an isomer of what we have above, where we have now a secondary radical, and again, the same H dot. So these two have the same number of carbons and hydrogens. The only difference is where the radical is situated. In our top example, this is a primary radical. In our bottom example, this is a secondary radical. And because it's secondary, it's more stable. Both of these reactions are endothermic. So if we are able to plot the energy of each reaction, what we would see is that it takes more energy to break the primary CH bond. It takes 410 kilojoules per mole to break this bond, and it only takes 397 kilojoules per mole to break the secondary CH bond. So because it requires less energy for this process to happen, it's more likely to happen. And that's just another way of thinking about the same thing. You can think about this in terms of the stability of the resulting radical, or you can think about it as the weakness of the CH bond. They're the same thing in different ways. This is important because we're going to talk about the energies of the reactions later. We're not going to do very much math or anything like that, but for one particular radical reaction, we are going to care about the energies involved. But what I also want you to be able to do is think about what's the most stable radical going to form if you have a molecule and you're breaking a CH bond. So if I asked you, what's the weakest CH bond in this molecule? Or if I asked you, what's the most stable radical that can form when we break a CH bond in this molecule, we would look at the same thing. We'd look at all of the CH bonds and see which one is likely to form the most stable radical. Here we are looking for primary, secondary, and tertiary. And we can see that we have one tertiary carbon. It's right here, and it has a CH on it. So that CH is going to be the weakest one in the molecule. That's the one that's going to form the most stable radical. So if we break this in the same way that we've broken the bonds above, what we would get to is something that looks like this. And this would be the most stable radical formed from this molecule. Now, I want you to practice this on your own with the molecules A and B over there. I want you to find the most stable radical that can form from cleavage of a CH bond. So hopefully you've paused the video and tried those examples. These are the kinds of examples you'll see on the exam. So here again, we're looking for tertiary carbons. So we have one here. This is the carbon. The most stable radical then is going to be the one that forms right here from the breaking of that CH bond. In our second molecule, we have a quaternary carbon here. That is the most substituted by far, but it does not have a CH bond to break, so it cannot form a radical. This one is a tertiary carbon. This can form a radical, so this is where we would form one. This CH bond here would break to give us this radical. And so those would be the answers.